This is part 3 of a series of videos about parametric curves. In this video, we're going to focus on animating straight line motion using the program Mathematica, which is what you see here. This is called the Mathematica notebook, using 3 Mathematica commands called listplot, table, and a new command called manipulate that will perform the animation for us. I hope you can still get a lot out of this as far as the math ideas, even if you don't have Mathematica. I think you'll still find it valuable. I'm also aiming this at students from pre-calculus through multivariable calculus as well as physics students. And I'm mostly using some ideas from a book called Multivariable Calculus by John Rogoski. This video is going to be a pretty challenging video, this part 3 here. I would definitely encourage you to go back to parts 0, 1, and 2 and watch those carefully, especially part 2. If you're going to understand part 3, you're also going to want to be ready to take notes or have Mathematica open or pause the video to try to understand things that I say. Listen very carefully to what I say in this video. It's going to be a challenging one. I do want to highlight one thing I did from the very first video, which was part 0, to illustrate why parametric curves are useful. They're useful in modeling motion, and here this code, this Mathematica code, will generate an animation that shows a basketball player shooting a jump shot, showing the ball hopefully going through the hoop as we see here, but we can shoot it at different angles, different initial angles, and different initial speeds to see what happens and experiment with that. The key to making that animation happen is this command right here called manipulate, and we want to illustrate that now in our main simpler example, our main foundational example, modeling straight line motion at a constant speed. We want to use parametric equations to model that. A person is traveling from the point 2, -1 to the point -1, 3 in 1 second. In the last video, part 2, we used these two functions, these two linear functions, f of t equals -3t plus 2 and g of t equals 4t minus 1, to give the x and y coordinates, the first and second coordinates of the point as the person moves. Where is the person as they move? Think about this. F of 0, look at that formula there, is 2. Make this bigger for you here. F of 0 is 2. -3 times 0 plus 2 is 2. That's the first coordinate of the starting point. F of 1, when you plug in t equals 1, you're going to get -3 plus 2 is -1. That's the first coordinate of the ending point. So F gives you the first coordinate of the point of where the person is at. G of 0 is -1. That's the second coordinate of the starting point. And G of 1 is 4 minus 1 is 3. That's the second coordinate of the ending point. These are linear functions. They will give you straight line motion at a constant speed. It turns out that if the speed is not constant, the functions don't have to be linear. But in this case, at a constant speed, we got linear functions. This command is a Mathematica command called table that will be used to generate points that can be plotted with listplot. Let me show you the output of this code right here. What you see there are 11 points showing the location of the person at every 1/10 of a second. Think about this. Maybe pause the video and make sure you understand why that's going on there. N is the iterator of the table command. It's starting at 0 and going up to 10, and it's assumed that it increments up by 1. That definitely is what table assumes, though you can change that. For example, I could increment it up by 2 instead, and we get fewer points. We get, what would that be? That would be 6 points instead of 11 points. But if you don't have anything there, it increments it up by 1. 0.1 times n gives you the actual time that you want to plug into f and g. For example, when n is 5, 0.1 times 5 is 0.5, and this is the point that the person is at after 0.5 seconds have gone by. We can embed this inside the list plot like you see down here. The table command is inside the list plot. So what Mathematica is going to do is it's going to first apply the table command. It works from inside out. It will generate this list that you see here, and then listplot plots that list. Okay, there we have the 11 points that are represented in this list up here. We also have different options that I showed you in the last couple videos to make the picture a little bit nicer. Let me show you, there's another option we can include here. Just to add a little color, I can put red, comma, before the point size and put this inside curly braces, and it makes the points red. That's kind of nice. All right. But the main thing we want to emphasize in this video is the use of a command called manipulate, like I showed you with the basketball. I'm going to embed all of this inside a manipulate. So I'll put the word manipulate in front of this, capital M, put square brackets, put an ending square bracket over here. I need to put a comma in there right before the ending square bracket as well, and it looks like I must have spelled it wrong. Yeah, okay, manipulate. There we go. And notice there's a little up arrow here, the little red up arrow, telling me I need more input. Now what is the input? Well, we need to understand what manipulate's going to do. Manipulate is a very flexible command that can be used to animate lots of different kinds of things. What I want to animate is I want to animate this motion. I want to see these points move, so to speak. I want to see the location of the person change as time goes by. I'm going to use the letter B for my animation parameter. The letter you use is kind of irrelevant, and something happened here. Get rid of this. Press the wrong button. B is going to be my animation parameter. I'm going to start it at 0 and go up to 10, just like I did with the N. However, unlike I did with the N, I need to put a comma 1 here to make sure that B increments up by 1 unit at a time, because manipulate's default, unlike table, is to assume the animation parameter is continuous. So if I don't put the comma 1 there, it's going to put fractional values for B in here, which actually could be okay in this case, but oftentimes it's not okay. By adding a comma 1 here, that's going to tell manipulate to make an animation where B goes up by 1 unit at a time. It increments up by 1 from 0 to 1 to 2 to 3, etc. And I think that's what I want to do. However, I can't just stop here. What is B doing? B is going to represent the ending value of N in the table command. I'm going to change this 10 to a B. Think about this. So first, think of the animation that is going to be made here as a series of snapshots. First, you're going to get a snapshot when B is 0. When B is 0, N is going to go from 0 to 0. It's going to be just 0, and you're just going to plot this 1 point, 2, -1. Then in the next snapshot, when B is 1, N will go from 0 to 1. It will be 0 first, then 1. It'll plot this point and the next point, which is the output of these functions at point 1. 1 times 0.1. The next snapshot occurs when B is 2. When B is 2, you get 0.1 times 2 is 0.2. It plots the first 3 points. So you're going to get a series of 11 snapshots showing more and more points as B increases. That's what's going to happen here. Go ahead and enter it. You see that the animation slider has been created here. I can open it up and I can play it now. And we see the motion as B goes from 0 to 10. First 0, then 1, then 2, then 3, then 4. We see the motion. Not in a continuous way, because this is still not ideal. We're still just plotting points. We see the motion every 10th of a second in real time, so to speak, but real time slowed down. You can speed this up, by the way, to make it seem more like real time. There we go. Let me also emphasize before I end this video that I could have also plotted more points closer together, say every hundredth of a second instead of every 10th of a second, by putting a 0.01 instead of a 0.1 in here, and letting B go from 0 to 100 instead of 0 to 10. Now we'll plot more points. It'll seem more like a continuous motion. So now we're actually plotting 101 points. B goes from 0 to 100 in increments of 1. Time is going from 0 to 1. It looks like a continuous line because there's so many points. There is our modeling of the motion. And with that, I'll end this video.